Oh, man, it did not like that. Okay, I'll have to mess with the YouTube channel again. They just keep changing that for some reason. It's very annoying. Okay, so right here's half lives. So your natural radioisotopes, these tend to have very long half lives. That's usually why you still find them. Okay. Alternatively, that's what you're seeing is natural isotopes that are built because you have particles coming in at very high energies from outer space, and so they are created in the atmosphere. Then, for example, nitrogen 14 is a major source of radioisotopes in nature. Okay, and it's actually nitrogen in the atmosphere getting hit by a neutron from space, particles from space. Okay. Okay, so these are some different naturally occurring radioisotopes, and you'll see they tend to have longer physical half lives. So that's why we actually encounter them in nature, because there's not really a process in nature to purify these radioisotopes. Radioisotopes are used in medicine and mostly by humans for very specific purposes, typically have very short half lives. That means the radioactivity is actually eliminated very quickly, right? That's why we actually don't have as much radiation problems as people fear and like to make people fear. Is that in fact most of the radioactive elements we make would be decayed within a month. So, yeah, we don't have a huge amount of buildup. Okay, so these right here are some of the ones that are used in medicine. You can see these are their physical half-lives. These would be the effective half-life if you were to feed somebody this, if it would enter their bodies. And you can notice that most of these are gone within about a month. Okay, so you're going to have half within 20 days, 28 days. Within another 28 days, you'd only have a quarter left, and so on. Okay. Some of these are actually quite short. In case you're ever wondering, has anybody been in a hospital and seen the little radiation sign? Yeah? Okay, so that little radiation sign area, if you're in a larger hospital, you'll see it has like a whole wing. And it's located in the basement usually. And it's like concrete walls all around. And that's because they're actually making these, right? Because you actually have to make these. I mean, kind of think about it. If they were to make these a year ahead of time, would there be any left when they're doing the test? No. In fact, this one, if they made it a day ahead of time, they probably won't have enough to actually run the test. Okay? That has to be made like for your appointment. And that's why, for example, if you ever get some of these tests run, they'll charge you whether you're there or not. It doesn't matter if you don't show up. You're getting charged because they had to make that radioisotope to run the test. And all that money and time already spent. Okay. And so there's a lot of the testing in hospitals are actually radioisotope testing, right? And we'll talk a little bit about nuclear transformations and how they're made in just a second here, okay? But let's talk about determining half-lives. So whenever you're working in half-lives, remember they're always going to be the time it takes you to half the sample, right? So if one half-life passes, how much of the sample remains? 50%, right? If two pass, how much remains? 25%, a quarter, right? 3, 12.5%, or an eighth, right? And it just keeps going like that each time. Okay, so the formula for half-life is this right here. It is the amount of isotope remaining. In this case, it would be a fraction amount. Okay? So it'd be like 1/4, 1/8, 1/16, etc. It is going to be equal to 1/2 to the n power, where n is the number of half-lives that passed. Now you can use a fraction here. So if you have 2.5 half-lives, you can put that in here. Okay? And it will work. Did anybody notice this is actually the same formula for compound interest? I know, right? Yes, so same formula. You multiply this by the starting amount. Typically, for most of your cases, that would be like 1 for the starting amount. but we could be given other units of starting amount. Like this sample had 30 disintegrations per second when it started. Well, that would be a starting amount. Okay. And so you can put that in here. It can be any kind of units, really. All right. So the next step is going to be determining the amount of isotope remaining. And that's the equation you do it. The easiest way to do this is literally just practice. And so we have phosphorus 32. This is a radioisotope used in leukemia therapy. It has a half-life of about 14 days. Approximately what percentage of a sample remains after 8 weeks? Anybody know why they use radioactive materials for cancer and leukemia therapies? No? Okay, so what's true about cancer? Anybody know what cancer is? Yeah, it's something that grows and grows and grows, right? And so there's two things that have to be true about that for it to do that, right? And that is, number one, it can't accept death signals, meaning it's immortal, okay? If you take a cancer out of somebody and just give it nutrients forever, it will live forever. And that's how those cell lines, you've heard of like the stem cell lines, that's how you make those, is you very selectively give it a specific type of cancer, okay? And those cell lines have outlived the people they made them from. For one of them is over 30 years older than the person that they made it from. The person died and it's been alive for 30 years past that. So if anybody asks you if you want to become immortal, no. Because that would just be body-wide cancer, right? Okay. And things would go wrong very quickly. The other thing that has to be true about cancer for it to grow so much is it has to take up nutrients way faster than your normal cell, right? Because it's going to need a lot of nutrients to grow, okay? And so cancer is pretty easily targetable by feeding poisons into the body that's poison to humans. And that's how they do basically every cancer treatment currently. There's some that are coming down the pipeline that are much better targeted. Really cool stuff. But for now... And so what ends up happening is they essentially feed you a poison. It's something that will accumulate in that type of cell that the cancer cell will be. The best treatments, they actually make a cocktail of poisons that are specifically targeting that. And they actually test it against the cancer cells to see which one's the best. Okay, that's a very expensive process. It will cost about $100,000 to treat you, just the testing part, not the full treatment. But it has a about 98% cure rate. So even on very difficult cases, okay? So it's very hard to get, but if you can get it, you have money, get that, okay? But so one of the things they do is they'll feed you like iodine or phosphorus, or they'll feed you a label on glucose that's radioactive that will accumulate in the cancer cells faster than your other cells. And it will cause the cancer cells to get killed off by the radiation because that's where it's accumulated. Okay. Lacking that, the ability to target it, they'll actually literally put a radioactive piece of metal in you. Uh-huh. Oh, most definitely. Yeah. The entire methodology of cancer treatment so far, there are some really great treatments we could talk about sometime, but it's more of a side conversation because it'll take a while. But so far, the cancer treatment methodology is essentially feed you poisons and kill the cancer faster than they kill you. Yeah. So, and that's true for all of this. Like surgery, cut the cancer out, and cut less of you than they do the cancer. Radiation beams hit the cancer more than they hit you. So that's true for all the treatment methods so far. Yeah, that's why they use like cyanide to treat some forms of cancer. I mean, cyanide is like the stereotypical poison, right? When you think of poison, probably cyanide. I actually worked with a coworker. That's how they treated her for her cancer. It's quite effective for certain types of cancer. Yeah. Okay. So again, we have a half-life of 14 days for this phosphorus 32. Approximately what percentage will remain after 8 weeks? Okay, so everybody got their attempt so far? Or did I totally overwhelm your ability to do the attempt with my Super interesting story. Okay. All right. Everybody make their attempt, the best attempt you can. By the way, we've actually been doing really well for time in this class. I've been really proud of you guys. Honestly. You're all rather focused and trying the problems, and I can see real progress being made. So it's been going good. Yeah, you guys are about to lap my high school class. I started a week before you. I told them that, and they're like, "Oh my goodness."
You also teach high school?
Yeah. So Green Hills High School has a early college program.
So dual.
It's just on their campus. Yeah. It's a really cool program, actually.
That's cool.
I really like that. Not as teasing my high school students. It's okay that they're getting get lapped. Everybody has different chapters that cause them different problems. So. It's chemistry. Eventually something will cause some problems. Okay, folks, let's go ahead and move forward. So, first thing you have to do is figure out how many days 18 weeks is, or how many weeks 14 days is. So, how many weeks is 14 days? 2. And so, how many half-lives do we have?
2.
Well, 8 divided by 2 would be? 4. So, we have 4 half-lives that'll be completed here, right? Okay, so you can use the formula, or I personally think that most people have more luck with just doing this logically. And so I have 4 half-lives, so I'm going to half it once. I'm going to half it again, which will be 1/4, right? I'm going to half it again, 1/8. I'm going to half it again, which is 1/16, yeah. Or another way of doing that is if you want it in percentages, 50, 25, 12.5, 6.25, right? You can tell I've done this a few times. I've just memorized them at this point. Okay. And so we halved that 100% 4 times. These are the same thing, by the way. And we get 1/16 times 100%, or 6.25%, right? By the way, this is the formulaic way of doing it. If you want to do it by formula, remember it's 1/2 to the nth power. We have 4 half-lives, so that's 4th power. Okay. Be careful if you do this on your calculator, though. If you put this in wrong, what you're going to end up doing is you might end up putting the power to the first and not to the 2 on the bottom. Okay. So you got to be careful when you do this. All right. In this case, you could actually just put the power to the 2nd on the bottom. It would work fine. Anybody know when it happens when you do the power to 1? So 1 to the power of? Yeah, you get 1 because it's 1 times 1 times 1 times whatever, right? Yeah. Okay, iodine 131 has a half-life of about 8 days. Approximately what fraction of sample remains after 20 days? This is where you definitely want to use the formula, okay? Because we have a portion of a half-life, right? It's not going to be full whole number half-lives. Doing this in your head is going to be very difficult for you to do because powers are difficult. Okay. All right. So how many half-lives have we covered? So 2 full ones, and then what? So 8 plus 8 is 16, right? We have 4 remaining, and then a half you got. Yeah. So 2.5 half-lives. Okay. And so we take our formula here, 0.5 to the nth power. We put our 2.5 up here, like so. And that's going to give us this as our fraction remaining. Now, again, that would be out of 1, right? If it's out of 100%, it'd be 17.7%, right? Okay. Okay. How long would it take for 85% of P32 to decay? Ooh, now I need to do the math in the reverse direction, don't I? Yep. So I'm probably going to set up my formula. Most people are going to find that the easiest way to do that. And this right here is the half-life. That's how you represent that. It's the time it takes for half of the material to disappear, right? And so equals 14 days. Okay, so 85% disappearing. What does that mean I have remaining? 15%, yeah. And so I need to get down to 15%, don't I? Okay. And so I'm going to end up putting in 15%. This is then going to end up like this. So my fraction remaining, that's 0.15 as a fraction, right? Okay. And that's going to be equal 0.5 to the nth power, because I need to figure out n in this case. I'm not going to have an actual number. Okay? Okay, so the next thing I'm going to do here is, well, I'm going to take the log of both sides. Okay? And when you take the log of something, you can actually take the power and you can bring it down in front of the log. Make sure you do the same log on both sides. Don't go ahead and put ln and log on one side. Okay? Does everybody know what ln is? That's the log base e. And it's different. This is the log base 10. Okay? So on your calculator, there's 2 logs. Careful that you don't mix them up. All right? Okay. And so this is going to be the log of 0.15. I have to use my calculator to do that because it's a little bit difficult for me to do that in my head. And that's going to be negative 0.824. I take the log of 0.5, and that's that number right there. Everybody okay with that one so far? Okay. Note that I brought my power out in front. All right. Okay. So now all I need to do is just take this number and divide both sides. So I divide both sides, it cancels off here, leaves me with this number above this number, which is that. I go ahead and do my math, and I get 2.74 half-lives. Okay. By the way, does that make sense? No?
Nope.
Okay, so first off, did anybody get stuck on the math?
Yep.
Okay. First off, let's talk about in terms of if this is a multiple choice, is there a faster way of doing this? Yes. Okay. You can do this logically. Okay, so I'm going to get down to 15%, right? Can I borrow a marker again? I'm sorry. Man, I just keep forgetting. The other rooms I teach in are so close. I'm going to have to give you a whole new marker again. I'm really slacking on the marker situation. Okay, so I have 15% remaining. Everybody's good with that, right? Okay. So I have to figure out how many half-lives have passed, right? So if one half-life passes, how much do I have remaining? 50%, half. If another one passes, how much do I have remaining? 25. Okay. If a third one passes, how much do I have remaining? 12 points. You got it. That's perfect. Yeah. 12.5%. Right. Well, that's too far, isn't it? Yeah. And so I'm something very close to 3, aren't I? So I would have guessed like a 2.7, 2.8 if I was guessing. If I had A, B, C, D, then I can actually narrow it down to one of these pretty easy, can't I? Yeah. Because I know it has to be something just under 3, right? Okay. You see how you can do this very easily, quickly, logically, and get close enough to get a multiple choice? Okay, let's talk about math. I'm going to do this long form since I feel like a lot of you are struggling with powers and logs. Okay? I know that it's not something. So theoretically, they teach this in the algebra, but I have never actually confirmed that. I know it's in the course description. Okay. So that's the formula we have so far. Is everybody good with that? That's the 0.15. That one's the 0.5 to the nth power, right? Okay, so we have to solve that some way, but powers can't just be brought down and multiplied, can they? Okay? Or another way of saying that is, if you were to do the opposite of a power, that's actually a root. You guys know that? Okay. So if you were to do the opposite of a power, what you'd actually end up doing is, I'll show you guys the opposite of a power. It'd be to the power of 1 over n, which doesn't really help us. Okay. Okay. So what's another way of doing this? Well, logs. Logs up. You take anything that's a power and bring it down, and that's because what a log is. Like if you were to take the log 10 here, okay, that would actually go to 1. Because what a log is how many powers is this? Base 10. So how many powers of 10 is this? Okay? Okay, so what we're going to do here is whenever you do something to one side, what do you have to do to the other side? The exact same thing, right? That's what math tells us. So I'm going to take the log of both sides. Now, because what this is doing is how many powers of 10, anytime you see something like this, where it's a power, you can bring that directly out in front. Okay? Is everybody okay with that part? All right. So I'm going to just rewrite one side so far. Okay, so now we have here numbers I can plug into a calculator and I can simplify. So what I'm going to do is I'm going to take my calculator. I'm going to plug in the log of 0.15. Okay? Depending on how your calculator, you might have to do a different way. If you have something like a TI-83 Plus, where you can like actually write out chemical different formulae, you can actually just write it like this: log parentheses 0.15 in parentheses as well. Okay. If you have some other calculators, you might have to put 0.15 and then hit the log button. Okay? It depends on the calculator. Practice. Use your calculator during homeworks and during classes so you get used to it, okay? It will betray you when you use it on a test if you don't practice with it. All right? And it will really mess you up. Okay? Okay, that's actually where these numbers came from right here. That's what I was doing. I just literally took my calculator and log of the number inside. Okay? Everybody good with that so far? Okay. Once I have the numbers, well, when I have a variable, this could have been x, this is n in this case, all I have to do is just divide that number over, right? Got it? Okay. Did anybody need me to go the rest of that, or are you good? Very good. Okay, so we have 2.74 half-lives. If we need the number of days, we're just going to take the 14 days times 2.74, and that would give us the number of days, which is 38 days. Okay. So nuclear radiation can be high energy particles or higher energy rays. Some radioisotopes of elements are going to be very useful for medical imaging. What's going to happen is some elements actually are going to concentrate in specific tissues. Excuse me. Now, the emitted radiation from those locations in the body then can be used, image. In the olden days, they'd use a photographic plate. They don't use photographic plates very often now. What they do is they have sensors that work like digital cameras. Okay. Though sometimes there are instruments where you could use a photographic plate. I don't think they use them anymore at all, but I don't want to say that expressly because they could. No, these can be detected by scanning sections of the body. You can get three-dimensional images by simply using three-dimensional plates. And so what that does then, and it gives you an exact location within that by overlaying those three-dimensional detectors. Okay. Now, it's very important to expose patients to the smallest possible dose of radiation for the shortest time possible. The two main uses for medical radioisotopes is number one, diagnosing disease states. And so this is very common for, it's how you do PET scans. This is actually how you do a lot of the scans, more than you probably think. Typically called tracers. The other one is therapeutically treating diseased tissues. And so that's what we were talking about when I was talking about killing cancer selectively. When diagnosing a disease state, the minimum amount of radioisotope with a very short half-life, the shortest effective half-life you can have, is going to be given to you. That's going to be referred to as a tracer. It doesn't need to just be that element. For example, one of the things that's more commonly used is actually glucose with a radioactive fluorine that's attached to it. Okay? Another one is technetium-99. Notice this is the M that's going to radiate a gamma ray. Okay? And so it's going to collapse down and give off a gamma ray here. So this can actually be used to diagnose proper blood flow through the lungs. Here we can actually see an example of this. And so this is what normal lungs look like. And you can see there's not a huge contrast between the regions. Okay? What you can see here is that you have here very cold spots that are within that lung structure. Okay? And so these are non-functioning areas of the lungs. They don't have proper blood flow, and so they have less technetium running through them. Okay? So that's what you're seeing. Kind of neat, huh? Ooh, ah. Right. By the way, see how this is just slightly different than that one period? That does happen from scan to scan. Depends on how much isotope you have, if they're actively breathing, etc. Okay? So there is some variance within spectra. And it's more the differences within the spectra that you're looking for. You can very much see like little cold spots intruding. In this, there's no like actual places jutting out, right? It's all sort of grayish. Okay, and so that's why there are cold spots there. On usually high areas of activity, like an area which the blood is being detained too long in the lungs, would actually show up as a hot spot. And so what you would have seen is something like this, but with like a really dark black spot. Okay, and that would be your hot spot. By the way, this is actually film right here. So these ones are actual film. That's why hot is a black color, whereas cold is the film color, right? So that's what you're looking for. Okay. So areas with rapidly dividing cancer cells will also retain extra tracer, and so they tend to show up as like hotspots. If you have a modern digital one, it's going to have like blue and red for hot and cold, right? Red for hot, blue for cold. Yeah. And then you have like shades in between, which are greens and yellows and stuff, right? So modern ones make it a little easier to see stuff. And in fact, even on film ones now, they actually use a digital system now that helps to like highlight spots for you to double check. So, radioisotopes can be used therapeutically, again, to destroy cancerous tissues. In the case of thyroid cancer, iodine-131 is a beta emitter. And so it's administered in doses that are about 1,000 times what you'd use to actually detect the disease, which would be your tracer dose. Okay. And in that case, iodine gets uptake by the thyroid cancer cells far more than the other cells. And so, interestingly enough, thyroid cancer is considered one of the easiest to treat cancers and has the highest success rate and the least impact on that person's life, like how long they're going to live. So, it's actually kind of an interesting one. That one's really well targeted and cured now. So cells that rapidly divide, of course, are going to be more susceptible to radiation, partially because the genetic material is more exposed, but also additionally because they're going to uptake more because they need more nutrients to actually divide. Okay. And so it basically is just a compounding effect on cancer cells whenever you target their uptake of nutrients. Okay. So it works quite well. All right. So let's talk about a couple of other treatment methodologies. There's external beam radiation therapy. This actually works a lot like how they irradiate your fruit. Did everybody know they irradiate your fruit? Okay. At the supermarket, if you buy the fruit at the supermarket, what they've done is they've used cobalt-60, just like this, and they have little rods that they then put above your fruit, and then they irradiate it with gamma rays. And those gamma rays kill off all the bacteria and stuff within the fruit, and it allows it to stay on the shelves for much longer. Okay? Now, interestingly enough, occasionally those rods break and then scatter cobalt-60 over things. That just happened like a couple months ago, and they had to recall a bunch of fruit. It may have been vegetables in that case, but you get the idea. Yeah. Anyways, so what's happening here is an external beam radiation. They're going to take 3 beams. They'll use cobalt-60, which is going to generate typically a beam of radiation. And what they'll do is they'll take the beams of radiation, they'll narrow them down into 3 different locations, the 3 different cardinal, X, Y, Z. And that is going to overlap in one spot, which is a tumor, which is then going to kill it by having very high radiation levels. Hopefully they don't hit anything else with that overlap of the 3 beams. Okay. By the way, my father actually underwent this to kill off a tumor, in case you're wondering. So this is brachytherapy. It's a small titanium seeds. It'll contain radioisotopes. What you do is you take these little seeds right here, the titanium seeds, and you literally implant them in tumors. And that kills the tumor around it. Once it's killed the tumor and shrunk that down, you remove the seed. Okay? Anybody have any questions about that? Kind of neat, right? Okay, let's talk about PET scans. Anybody know why that's funny? It is. It's scan. So don't forget to make fun of your doctors. Yeah, scan. Okay, so PET scan, this stands for positron emission tomography. So it's going to identify functional abnormalities in organs and tissue. How it's going to do this is you'll have fluorine-18 that's going to be present in a tracer that's used for a PET scan. It has a half-life of 110 minutes. Again, this has to be made and ready for your specific scan. Okay? That's one of the reasons why you end up showing up. Basically, what they do is they wait for you to show up, and then you have to sit there waiting to do the scan for about 2 hours. Guess why it's about 2 hours?
They're making it.
They are. Yeah, they're making it. Or getting it shipped from the place that's made nearby. Yeah. So the half-life is 110 minutes. The fluorine isotope is going to emit a positron. It'll decay to oxygen-18. That positron, whenever it hits an electron in your cells, is going to then flash and make a burst of gamma rays. And that gamma radiation flash is going to be detected by scanners. Typically what it is, a series of 3 scanners in the XYZ directions. It allows them to pinpoint where that burst happened. And so then they get a nice picture of those bursts, and then it gives them an overall picture of, say, your brain. Okay? And where that glucose is going in your brain. Okay. Very commonly used for the brain because Anybody know what the brain eats? The only form of energy it eats?
It likes ketones.
It likes glucose.
It also likes ketones. And it can
It
use that
uses ketones.
as
It
energy.
builds glucose. Yeah, and it's actually not the brain that does that.
Okay.
Your body uses ketones to build glucose.
If
And then
ketones are
your-
present and no glucose is present, our body will still choose ketones over glucose.
No. What happens is it actually builds those up into sugars.
Yep.
So it's not that your brain actually uses glucose
Mhm.
for energy, but there are a few ketones that can go in directly into pathways, but they're quite unusual. And your brain's unusual because it actually only uses glucose. It doesn't use fats at all.
That is not what I have learned.
So it doesn't directly use fats, but what it can do is your body, particularly in your liver,
Mhm.
will process those ketones into glucose and then spread that throughout your body.
Okay.
So that's typically how your body mostly uses ketones, though there are spots in your body that can use ketones directly. For example, like your muscles. Yeah. So they can directly shortcut. Though they still normally use mostly glucose anyways. Yeah. So anyways. This right here is your study guide. And we'll go ahead and go on to the next chapter. We are making pretty good time.